Alright, this is Spring 2010, quiz number 3, problem number 3. So we're given an incomplete table which lists control signals for several instructions on an unpipelined beta. And we've got the beta right here. Okay, and we want to consult the beta diagram and the instruction set summary right here for reference. So the operations include 2 existing instructions, so that means 2 things from any of these, and 3 proposed additions to the instruction set. So these 3. Now, in the following table, we can use dash dash to represent don't care, Z, or 0 or 1. Z being the output from this 32-bit NOR right there. And in each case, we want to give we want to enter an opcode, a value, an expression, or dash dash. So by opcode, you know, we can enter stuff like LDX or add or something if that was one of the instructions. Okay? So first thing we want to do is try and figure out by process of elimination which the 2 existing instructions are. So if we notice, the load double indexed, the move a constant into a register if it's 0, and store relative are all operations that just go to PC plus 4. So because of that, and we can observe that these 2 operations do change the PC to something other than this little PC plus 4 path right there. So we know that they're going to be the 2 existing instructions. So start off, we say PC cell is 2, PC cell is 2, when we're doing a jump instruction, right? That's when it takes that jump target. So we know that this must be JMP. And when a jump instruction happens, we want to save PC plus 4 through the WD cell mux and into the register file. And in order for that save to happen, WRF needs to be 1. So we'll have WRF be 1. Now, the next instruction sets PC cell to Z. So Z can either be 0 or 1, right? Right here. Z is 1 when the value coming out of register A is all zeros. So that would make PC change to 1 whenever register A was full of zeros. Change the PC if something's equal to 0. That sounds like a BEQ instruction, right? So BEQ. And the rest of that table is filled out for us. So now we know that the other 2 here are going to be either MBZC or STR. So let's start with LDX. So a load double indexed is just going to calculate a memory address from which to load based on register B contents and register A contents. So a regular load takes register A plus this signed extended literal here, and then down here that's the effective address. But instead, the load double indexed is just, instead of this constant, it's just going to take the value from the B register. So the only thing that we need to change from the way a regular load's done is just set B cell to 0 instead. So B cell can be 0. WD cell should be 2 because we want to get data out of memory and into the register file. Okay, and then the ALU signals, we're going to have A and B, and we're going to add them to get an effective address, right? Because this said we're going to add over here. So we know that we want that to be plus. Okay. Now we have either, so this one's done. Now we have either MBZ constant, so we're going to move, if there's, move a constant into a register if the other register has 0 in it. So looks like deciding whether or not to do something based on Z here probably would be this instruction, right? Because we're basing something on whether register A's contents are equal to 0, which is what Z is for. So using that information, if WRF is set to Z, that means that you can do whatever operation you want here, right? And you'll have your answer waiting to get into the reg file, but it'll only commit if register A was 0. In other words, if Z was 1. That's why we set warp equal to Z. So this must be M, V, Z, C. And it looks like all the rest of that is filled in for us, right? We just want to take B through the ALU and then commit it if it's Z. Alright, so the last one must be store relative. So store relative is going to work like a regular store, except it's going to take the same kind of address here that a load relative does. So this is PC plus 4 times sign extended literal. Going to go through the A cell mux. So A cell should be 1, and it is. That's good. And then we're going to set the ALU bits to be A, so we don't care about B cell. So we should make sure that we indicate that as a don't care. It's important to know that we can do whatever we want with that. So that's our memory address, and then we're going to save something from register B here into data memory. That's our write data. And then we're not getting anything out, so we don't care about WD cell either. And because we're not getting anything out, anything that's on this wire should not be committed, so WRF should remain 0. The WR signal here needs to be 1 because we have to be able to write to memory. And then just like a regular store operation, we want to be writing the data from register C into the memory. So the way that we read data from register C is by setting RA2 cell to 1.